Good morning, all of you. My name is Sai Kiran. I am your chemistry lecturer. If you remember, in our last class, we discussed particle nature of electromagnetic radiation. In that, we covered black body radiation, Planck's quantum theory, photoelectric effect. Today, we shall be discussing about second development towards Bohr's model, that is atomic spectra. And the second topic is detailed explanation of hydrogen spectrum. Now, we start with spectrum. This is the source of white light, and this is prism and photographic plate. Initially, this plate is black in color. Let's assume this is in black in color. Let's understand. When white light is passing through the prism, it splits into 7 colors. We know that with GR, in which each color has a particular wavelength. Now we can see on this photographic plate, here we can see violet is present, and here indigo color is present, here blue color, here green, here yellow color, here orange, here red. I got radiations of different wavelengths on this photographic plate. This is called spectrum. Spectrum is nothing but the collection of radiations of different wavelengths is called spectrum. We have two types of spectrums. One is continuous spectrum. And second one is discontinuous spectrum. Now, continuous spectrum. The spectrum having all colors are merged. In between these colors, there is no gap or lines. That spectrum is called continuous spectrum. For example, rainbow. Rainbow forms in the sky. In rainbow, the colors all are merged. There is no gaps or lines between the colors. That is the example of continuous spectrum. Now, discontinuous spectrum. The spectrum having distinct, well-defined lines or gaps between the colors. For example, violet is up to here, and indigo is up to here, blue is up to here green, yellow, orange, red. In between these colors, particular lines or gaps is present. That spectrum is called discontinuous spectrum. The discontinuous spectrum we can classify into two types. One is absorption spectrum. And second one is emission spectrum. Now come to the absorption spectrum. The spectrum formed due to after absorption of radiation. Let's understand. It is the sample which I am taking. It is made up of atoms. We know that atoms have electrons. When white light passing through this sample, the atoms absorb radiations of some wavelengths, due to which the electrons are excited from lower energy state to higher energy state. Now, for example, this sample absorbs indigo radiation and yellow radiation. After that, this light passing through the prism, it splits into colors. Now, this plate showing here violet. In the place of indigo, there is no presence of indigo here because that indigo radiation is absorbed by the sample. Now it's showing empty space. Initially this plate is black in color, so here it shows black color, which means empty space. There is no color present in this part. Here blue color, here green. Similarly here yellow is absent because this yellow is absorbed by the sample. So here also showing black color, which means empty space. Here orange and red. These two wavelengths are used for excitation of electrons. That's why we have got black lines on this plate. This is called absorption spectrum. It contains black lines or dark lines on colored background. This plate is filled with colors. These two black lines are present on the plate. So black lines or dark lines on colored background. This is the absorption spectrum. Now come to the emission spectrum. Emission spectrum is formed due to emission of radiation. In previous case, electrons absorb energy and gets excited state. In excited state, they are unstable. So they come back to the ground state. In this process, they emit same amount of energy which they got absorbed. This radiation is passing through the prism. On photographic plate, we can observe indigo color is present here and yellow is present here. And remaining colors are absent because these two colors are observed by the sample. So remaining plate shows black in color. Which means empty space. There is no color present on it. This is the emission spectrum. Emission spectrum contains colored lines on dark background. The plate is in dark color. Only these two color lines are present on this plate. Colored lines on dark background. This is emission spectrum. When compared to emission spectrum with absorption spectrum, these two are photonegative of each other. The study of emission spectrum or absorption spectrum is called spectroscopy. Now, this emission spectrum further classified into two types. One is line spectrum and the another one is band spectrum. Line spectrum, it has distinct well-defined lines like this. This is called line spectrum. It was formed by atoms, so we call it as atomic spectrum. Each element has a unique line spectrum. It is used to identify the unknown atoms. In the same way like fingerprints are used to identify the people. This is the line spectrum. Now come to the band spectrum. It's look like the spectrum having closed packing lines. This is called band spectrum. It was formed by molecules, so we call it as molecular spectrum. This band spectrum is formed due to vibrations and rotational changes of atoms in a molecule. For example, in water molecule, 2 hydrogens and 1 oxygen is present. These atoms have some vibrational and rotational movements. Due to some vibrational and rotational changes, this band spectrum is formed. Now come to the second topic, the line emission spectrum of hydrogen. Hydrogen has only one electron, so its spectrum is simple. Let's understand the experiment. This is discharge tube and this is prism, this is photographic plate. When hydrogen gas is subjected to electric discharge tube by supplying high voltage, it produces bright light. The light passing through the prism, it splits into different colors. These are observed on photographic plate. This is called hydrogen spectrum. Let's understand what happened inside this discharge tube. Now, when I am supplying high voltage, these electrons absorb energy and goes to the higher energy levels. For example, this is the ground state. Initially, electron is present here. These are higher energy states, excited states. When I am supplying some energy, this electron absorbs the energy and goes to the any one of higher energy levels. This is called excited state. In this, the electron stays only a small interval of time. That is, 10 to the power of minus 8 seconds. Because it is unstable in excited state. Hence, it comes back to the ground state. While coming back, it emits energy in the form of radiation. The radiation forms spectral lines like this in various regions. This is the hydrogen spectrum. Hydrogen spectrum have 5 series of lines. Let's understand with diagram. Line spectrum of hydrogen. This n value indicates the number of shell. This n is equal to 1 is first shell, n is equal to 2 second shell, n is equal to 3 third shell, n is equal to 4 fourth shell. Similarly, fifth shell, sixth shell, seventh shell, up to infinity shells. This also indicated with K, K shell, L shell, M shell, N shell, and so on. When an electron make a transition from any one of higher orbit to the first shell, we call it as Lyman series. It is observed in UV region, ultraviolet region. When an electron make a transition from any one of higher orbit to the second shell, we call it as Balmer series. It is observed in visible region. When an electron make a transition from any one of higher orbit to the third orbit or third shell, we call it as Paschen series. It is observed in IR region. Similarly, from higher excited state, any one of higher excited state to fourth shell, it is called bracket series, observed in IR region. Similarly, Pond series, observed in IR region. This is called first line of Lyman series. It is also called H alpha of Lyman series or K alpha of Lyman series. This is called second line of Lyman series. It is also called H beta of Lyman series. This is third line of Lyman series. It is called H gamma of Lyman series. Similarly, this is fourth line of Lyman series. It is called H delta of Lyman series. Similarly, this is the first line of Balmer series. This is also called H alpha of Balmer series. Similarly, H beta, H gamma, H delta. Similarly, this is H alpha, first line of Paschen series. H alpha, H beta, H gamma, and so on. In sometimes question they ask, electron make a transition from H alpha line of Lyman series, which indicates N1 ground state is 1 and N2 excited state is H alpha means first line, so second. For example, when an electron make a transition from H gamma series of Lyman series, H gamma indicates N1 is equals to ground state 1, N2 is gamma, this is alpha, beta, gamma, N is equals to 4. Fourth one is excited state. This is the light spectrum of hydrogen. As N value increases, energy increases. We know that according to Planck's theory, E is equals to hc by lambda. H is Planck's constant, C is speed of light. These two are constants. Now I want to remove the constant. Proportional sign is come. E is inversely proportional to lambda, which means energy increases, lambda decreases. In this, as N value increases, energy is also increases. As energy increases, lambda value wavelength is decreases. Now I want to make a tabular form to easily understand and remember these series. Now the first one is Lyman series. It is observed in UV region, ultraviolet region. The ground state is 1 and excited states are 2, 3, 4, 5, 6 and so on. Similarly, second one is Balmer series. Region is visible region. Ground state is second. Excited states are 3, 4, 5, 6, 7 and so on. And next one is constant series. Observed in higher region. Ground state is 3. Excited states are 4, 5, 6, 7 and so on. And next, bracket. Observed in higher region. Ground state is 4. Excited states are 5, 6, 7, 8 and so on. Next, fifth one is fund series. It is observed in higher region. Ground state is 5th and excited states are 6, 7, 8 and so on. These are the series and regions and ground states and excited states. Wave number or wavelength or frequency of spectral lines of hydrogen atom can be calculated by using Rayberg's equation. That is, mu bar equals to 1 by lambda, that is equals to RH into Z square 1 by N1 square minus 1 by N2 square. This is the Rayberg's equation. In this, mu bar is the wave number, lambda is the wavelength, RH is the Rayberg's constant, that equals to 1.097 into 10 to the power minus 7 meter inverse. And Z is the atomic number, N is the lower energy level, N1 is the lower energy level, N2 is equals to higher energy level. Now come to the calculation of line of longest wavelength or line of shortest energy. For that we have formula. Mu bar max equals to 1 by lambda max equals to RH into 1 by N1 square minus 1 by N1 plus 1 whole square. For example, H alpha line of Lyman series. Electron make a transition from H alpha line of Lyman series. It is nothing but first line of Lyman series. 1 by lambda max is equals to Rayberg's constant into 1 by 1 square. First line means N1 is equals to 1 minus 1 by 1 plus 1 whole square. Here RH is 2 square. 2 square means 4 minus 1, 3 by 4. By putting Rayberg's constant value, we can calculate longest wavelength of Lyman series. Let's see the calculation of line of shortest wavelength or line of longest energy. It is also called series limit. We have a formula for that. Mu bar minimum, that is equals to 1 by lambda minimum, that equals to Rayberg's constant into 1 by N1 square. For example, H alpha line of Balmer series. Electron make a transition from H alpha line of Balmer series. It is nothing but first line of Balmer series, in which N1 is equals to 2. One by lambda minimum is equals to Rayberg's constant by 2 square, that is equals to RH by 4. By putting Rayberg's constant value, we can calculate line of shortest wavelength. Let's see the calculation of maximum number of spectral lines formed in a spectra. For that, we have a formula N2 minus N1 into N2 minus N1 plus 1 divided by 2. For example, electron make a transition from higher level 6 to 1. In this, 6 is N2 and 1 is N1. Substituting this formula, 6 minus 1 into 6 minus 1 plus 1 divided by 2. That is equals to 5 into 6 by 2. That equals 30 by 2. Maximum number of spectral lines formed is 15 when an electron make a transition from 6 to 1. Now, I want to calculate maximum number of spectral lines formed in a particular series. Number of spectral lines formed in a particular series. Like Lyman series, Balmer series, partial series, quant series. For Lyman series, formula is N2 minus N1. That equals to N2 is 6 minus N1, 1. That equals to 5. For Balmer series, excited state is 6. Ground state is 2, 4. Partial series, excited state is 6. Ground state is 3. Bracket series, 6. Ground state is 4. That equals to 2. Fund series, 6 minus 5, that equals to 1. The sum of these is equals to 15. 5 plus 4, 9, 9 plus 3, 12, 12 plus 2, 14, 14 plus 1, 15. Maximum number of spectral lines formed in a spectra is 15. In this, 5 spectral lines are formed in Lyman series, 4 spectral lines are formed in Balmer series, 3 spectral lines are formed in Parston series, 2 spectral lines are formed in bracket series, 1 spectral line formed in Punnett series. That's it today class. In our next class, we will discuss Bohr's atomic model of atom.